Hi, in a video not that long ago I tore down this medical devices grade plug pack. It's like a normal mains plug pack, but it was designed for medical applications, and hence it had extra safety requirements and insulation requirements between primary, secondary, and stuff like that to meet various medical safety standards. Anyway, one of my viewers, Azar, he's from Iraq actually, so hi to all my Iraqi viewers. Fantastic, I do actually have a few. Now, he actually wanted to know what is this thing on the PCB down here, and I called it a spark gap, and that's exactly what it is. But he wanted to know what is the function of these and why would you put it on a PCB? Well, let's take a quick look at it. Now, as you can see, what it is basically two bare traces like this. They just happen to be in like a weird semicircle, and then this sort of point arrangement like this, which is quite unusual. I haven't actually seen one exactly like this before, but anyone does them slightly differently, which we'll go into. Anyway, they all have something in common, these spark gaps. They've got exposed metal traces like this, in this case solder coated, or they could be whatever, but anyway, they're exposed and the solder mask is exposed like that, and there's a tiny gap between the two like that. And the reason it's called a spark gap is because they're designed to arc over. When you get a high voltage between this point here and this point down here, instead of destroying your components, the idea is that this arcs over and you get a spark across the smallest gap there. Now, there's many different ways to protect your product and circuit against ESD discharges into your product on an input pin, for example, or some sort of overload pulse or lightning strike or whatever. And this is just one of the techniques. In fact, this is one of the crudest techniques, but it has the advantage of being effectively free, because you already get making the PCB, so it doesn't cost you anything to add one of these spark gaps onto here. It just costs you a bit of board area on your PCB, that's all. So if you've got the room to do it, this can be a cheap and simple, but and reasonably effective way to protect your circuit and board against electrostatic discharge or high voltage overload, lightning strikes, things like that. Now, of course, I'll say up front that this is not the best technique to do. It is basically a poor man's way to protect your inputs, and on its own, it's probably not that great. And it's not recommended that you use just a spark gap on its own. But hey, it's better than having no input protection at all. Now, the more professional ways to protect your input, of course, and sorry, this won't be a tutorial on how to protect your inputs. I'll have to do a separate video on that. But you can use things like gas discharge tubes, you can use MOVs and TVS devices. Now, this gas discharge tube, or GDT here, is actually a spark gap. It's just a much more controlled way to do it than just your crappy little PCB on here like this, because this is quite uncontrolled. You don't really have much say in what the exact breakdown voltage will be and things like that. Whereas with a properly specified gas discharge tube like this, you will, it'll be actually tightly controlled. It'll be tested and engineered properly, but it's essentially the same thing. What's inside there is a really well controlled and well engineered version of that. But of course, gas discharge tubes and MOVs and TVS devices, they all cost money, whereas this costs you absolutely nothing. So the way they work is incredibly simple. When you've got free air like this between two conductors, well, at a certain voltage, then it's going to arc over. You're going to get that spark, just like you get a static shock. You walk across the carpet, you're rubbing your feet, you're building up a static charge, and you get near the doorknob and you see that spark jump across. Well, that's because you can build up tens of thousands of volts static charge, and well, tens of thousands of volts is quite a lot of voltage, and that will easily jump across a spark gap like this, because you're so used to seeing, quite long spark trails. So when you get them really close like this, you can get reasonably low voltages. By reasonably low, I mean like 1500 or 2000 volts. You pretty much can't get under that, and that pretty much is a minimum. Let's just do like a rule of thumb, like 2000 volts, for example, might be a minimum that you do here, purely based on the fact that there's only so close that you can make these without risking them shorting out. So you've got to meet your PCB design rules, your clearance rules, and that's generally how you would design this thing. You would design it if you're designing an 8 thou board, for example, 8 thou clearance, or 0.2 millimeters clearance, for example, then that's what you would set your minimum spark gap distance here. But like I said, these are actually highly variable. That's why they're a poor man's spark gap. But there is somewhat of a formula that can help you estimate, but it's going to be very rough. And this formula is thrown around in the odd place. They would have derived this from experiment, so it's not hugely theoretical, but it's based on the atmospheric pressure because it's going to change. So in low pressure atmospheres, i.e. when you climb up the top of a mountain, for example, you can have that lower pressure, and let's say you've got half the pressure, then that figure is multiplied by half, so you're actually going to have a lower breakdown voltage at those higher atmospheres. So that's actually reasonably advantageous for things like these spark gaps. But when you're actually designing and laying out boards, I've mentioned this before, when you actually want to keep a minimum clearance between here, it's really going to matter at what pressure you have to keep a larger distance here at a higher altitude. Anyway, the basic formula, rough formula here, is the breakdown voltage is equal to 3000 times the pressure in atmosphere. Usually you just take this as 1. So, like at sea level, you've got 1 atmosphere of pressure, and then the distance in millimeters plus 1350 here, and that works out to, well, if you've got like an 8 thou space in, for example, which is around 0.2 millimeters, then you're going to get around about 2 kilovolts, 2000 volts breakdown. And if you're sort of like the lowest geometry, like 4 thou, you can go down to on a regular board, it's going to be at least 1500 volts. But hey, these things can vary. It's going to depend upon the exact geometry, etching, over etching, things like that, contamination of the board, whether or not it's already arced over before, and whether or not anything's carbonized. So anyway, enough of that. Let's actually put a high voltage across this, see if we can get it to spark. Okay, so what I've got here is my Uni-T UT513 5 kilovolt mega insulation tester. So it'll allow us to go, it only allows us to do basically 1000, 2500 or 5000 volts, but hey, this will let us spark it over, and it's got a reasonable amount of energy behind it as well, so it should hopefully continue to spark, not just like a static discharge. For example, when you build up on yourself, yeah, it can get 20 kilovolts or something like that, but hey, it's all over Red Rover once you discharge it. But this thing should hopefully can continue to spark this thing over. Okay, here we go. I've got it set to 500 volts, so we'll start out low and we shouldn't get any arc over at all. Yes, I have scraped away some of the tracks there just so it doesn't run off and discharge somewhere else. So hopefully, here we go. Let's test 500 volts. Nope, nothing. All right, and here we go. This is 1000 volts. Nope, nothing at all. Didn't expect it to, because as I said, pretty much minimum, but it depends on contamination and all sorts of stuff. But generally it's going to be, like 2 kilovolts or something. Now, here we go. Here is where I expect it to possibly arc over, although it may not. There is a lot of tolerance. I don't know what the gap is down in there. Looks quite large, so wouldn't surprise me if this doesn't arc over, but it might. So here we go. This is 2500 volts. Hey, look at that, we got it, and it's shut off. There you go. Yeah, so the insulation tester just shut down there, so it must have been overcurrent, and it shut down to protect. Anyway, let's go higher. Let's ramp it up to 5 kilovolts. Here we go. Here's our maximum. It did last for like a second or two before though, but let's give this a whirl. Oh yeah, look at that, and it's switched off. Now you can see the carbonization of that trace. Look, you can see we've got some carbonization down in there between that point and that point. And that is the problem with, hey, no pun intended, points like this. When you have very sharp points, it can often be a one-shot deal like this, especially for high energy, reasonably high energy devices like this insulation resistance tester. If it arcs over like that and does it for a couple of seconds, then you can get some carbonization, and then, well, your board could be pretty much toast. So yeah, they could actually short out, so you've got to be careful. So in theory, sharp points are the way to go because as you saw, the spark will come to that sharp point. But in practice, it's not that great because it can lead to little carbonized tracks like we just saw here. That's neat. Now that's got a little bit of carbon there. Let's go back and test 1,000 volts again. It'll probably be okay, but I just want to test it out of curiosity. No, there we go. But let's try 2.5 kilovolts again. Yeah. Haha, love it. But things like ESD, electrostatic discharge, they're not going to be huge amounts of energy like this. So they're just going to like spark over once and boom, that's it. It absorbs all the energy out of it. And that's the whole idea of these things, is to take out the energy before it reaches your circuit. So generally, this isn't the best example here, but generally these would be right near your input connector, for example, going down to ground. And I'll show you that in a minute. And then you'd have the trace leading off to your chip over here because you want the energy to be dissipated right at your input connector where the impulse actually happens. You don't want to like put it after your chip because then by the time it gets to your chip, you're going to blow your chip. And here's another example. Here I've just got another mains power supply I pulled from another teardown, and yeah, it has one of these jaw type ones over here. Now this one's not particularly good practice because once again it uses the sharp points like this, even though it uses multiple ones like this. There's no solder mask removed in there at all. They haven't actually taken it out, and that's not good practice. You're supposed to take the solder mask out, and certainly you don't want to cover the whole thing in solder mask because this doesn't work. It relies upon the fact that there's free air on actually between the two traces, and when you cover the things with solder mask, that's why this gap here, even if this trace came to within close to here, it wouldn't spark across here. It'd spark across here first because it's an air gap and not and because the solder mask on here actually provides really good insulation between the two. So in this particular case, that was actually between, I've taken out the transformer, it was between the primary and the secondary of the transformer here. Anyway, let's spark this one over. Okay, let's go 500 volts. And as usual, you don't expect anything, even though it looks pretty crusty in there. And 1,000 volts. No, it's still holding in there. And here we go, 2,500 volts. Whoa, look at that center one. And this isn't switching off the meter, so it's just continually going. Look at that. So it's just going to burn a trace in there. It's just going to burn the board and leave a horrible carbonized trace behind there. That's fantastic. Look at that. Let's go to, oh, there we go. There we go. It burnt. There you go. It actually fried that sharp point, and then bingo, the next one took over. So this was the idea, but oh yeah, there we go. Now it's doing a dance. And the meter just switched off. Haha, brilliant. But yeah, look what's left behind. See, there you go. You can really see the carbonized ends of that thing. I don't know if it's left a trail there on the board itself, but yeah, yep. Those three aren't as functional as they once were. And we didn't get around to testing 5 kilovolts. Here we go. Yeah. Alright, so how do you do this when you're actually laying out a board? Well, as I've said, everyone has their own way of doing it, and there's pros and cons, and you could argue until the cows come home about this. But anyway, I showed you just a couple of simple methods. And now what we've got here on the right-hand side is our I/O connector that we want to protect, for example, from ESD, and we've got our chip over here. Now, we don't want to put our spark gap over here on the chip. You want it to be over here on the connector, as close to the connector as possible, so that energy is absorbed at the connector before it has a chance to propagate along here and go into your chip. And yes, we're not going to have any extra input protection for the chip. We're just going absolute tight ass, poor man's spark gap. So what we can do is on the layer here, we can place a wrong layer. Here we go. So what we can do is we can go in here and we can place a fill. You'll see this reasonably often, and then we go to our which of course will be our ground. You would set that to your ground net, and then we can go to our top solder mask, and we can place a corresponding fill over here so that our solder mask is removed on these points here, and it might not look obvious at the moment, but if we go into 3D view, bingo, I've removed the top silk screen, and this is what you get. There you go. So we've got, you can see that here's our pad here, and we've effectively created a little spark gap in there. So we've got this exposed, it's shown as gold here, that's copper or your gold plate or your tin plate or whatever it is. So we've removed our solder mask around there, and we've created that little gap in there. So if this is like an 8/8 board, for example, really quite crude, but a typical one you might have, then you would set your minimum design spacing in there to 8 thou or 8 mil. So not to be, when a mil, I say 1/1000th of an inch, it equals a thou. It doesn't equal millimeters. I'm talking imperial here. Or, you know, if you talk metric, you're laying out your boards in metric, it could be 0.2 millimeters, for example, would be a spacing in there. So there you go, you've created that little spark gap across there, but you know, that's probably not the best solution, but you'll see this actually quite common in various products. You've seen them probably in a couple of teardowns I've done where they've just removed the solder mask. It's just easy and lazy way to do it from a layout point of view, but hey, crude but effective. Alright, so let me show you a slightly better method just to avoid that point source that we got before with the pad in there, and you know, it just wasn't as controlled as you'd generally like. So what I've done here is I've extended a track out from each one of these, equal length like that, so every pin that you want to protect, and then we're going to place a polygon pour. Okay, so this would be connected to your ground net, but I don't have all the, you know, an actual project set up with nets, but that's what you connect it to, your ground. So we'd go in here, and then we'd create our polygon. You can do this as part of your, like, just your usual ground fill on your board, but here we go, and we've already set up our design rules for 8 thou, so it automatically creates the spacing around that trace with 8 thou. Now, of course, if we go over to our 3D view, the solder mask is there, and it's not going to work, okay? That solder mask is going to insulate that completely, so what we want to do, of course, is go to our top solder mask, and then we just want to place a solder mask fill on there. Don't go all the way to there. Let's just go, say, from there to there. Should do the trick. And if we go over to here, bingo, look at this. We now have a very nice, completely rounded one like that. So, you know, really there's no sharp point to sort of, you know, wear out and all that sort of stuff. So it should be fairly evenly distributed, as we saw in the video before. It should just sort of like spark around in any sort of random location. So that one is, you know, is pretty ideal. But as I said, you could argue the pros and cons about this you know, until the cows come home. Everyone's got their own favorite method. Some people will say like a square-ended track in there is better, and well, that's okay too. But yeah, you know, something like this. That's just a couple of different methods to do that. Like I said before, the whole point of this is to basically clamp the energy, get it to spark over right at the input connector where that transient is going to happen. The last thing you want to do is for it to propagate along this trace and go into your IC pin. So if you can clamp the energy right at your input pin, that is the place to do it. And of course, good design practice. As I said, you would generally put some extra protection on the input pins, although the ICs generally, you know, fairly robust in terms of ESD these days. Not perfect, but, you know, they're pretty darn good. So often just adding a spark gap like this, not too bad at all. But the best part about this is that it is free. It only costs you board space and a couple of minutes of your time at the layout stage, and bingo, you've got at least some form of crude spark gap protection for ESD or other surges. You know, yeah, it has limited use, but it's better than nothing. So, hey, why not add it to your next design? And there's many different ways to do it. Hey, pick your favorite flavor, but as long as you got something, you know, it's better than nothing at all. So I hope you enjoyed that video and found it somewhat useful. If you want to discuss it, jump on over to the EEVblog forum. That's the place to do it. But hey, YouTube comments are cool too. And if you like it, please give it a big thumbs up on YouTube, because that helps a lot. Catch you next time.
Oh, by the way, just a quick plug, if I may. I'm now accepting donations via Patreon. So there's a whole bunch of benefits to this over PayPal. For those who are thinking about donating, you don't have to, of course. I'm happy just to have your viewership. But for those who have been asking, I had people ask, can I set up Patreon? So I have done that, and you can accept donations through there. So you can donate to your favorite bloggers and stuff like that. There's a lot of people on there, and it's really good. It just allows me to interact with my backers a bit better. It's much better than PayPal. It's more visible. Anyway, link down below if you want to do that. Thanks.